One of the reasons stoichiometry is such a powerful process for us to really get locked in is because it can be applied in a lot of different ways. And if we know how to do that one process and then can apply it to a lot of different problems, it can make some of those new problems seem a little bit less new. So now we're going to take a look at how we can apply the stoichiometry process to a thermochemistry problem. So let's take a look at an example. Consider a thermochemical equation. This is the burning of glucose. Glucose reacts with oxygen to give us carbon dioxide and water and 670 kilocalories of energy. So how much heat is generated by digesting? Digesting is just the biological process that's the analog of burning. 1.742 kilograms of glucose. So if we recognize this as a stoichiometry problem, we can approach it using the same 4 steps that we use for every other stoichiometry problem. So step 1, write a balanced chemical equation. Step 2, find moles of whatever you can find moles of. Step 3, use the relationships in the balanced chemical equation to convert moles of known to moles of interest. And then finally, convert moles of interest into the quantity of interest. And often that's grams, but sometimes it ends up being heat. So how do we apply these steps to a thermochemistry problem? Well, let's do our steps. We've already got a balanced equation. That's great. It's the thermochemical equation, so it even has a little bit more information in it. Let's convert to moles. The only thing we really know much about right now is 1.742 kilograms of glucose. So 1.742 kilograms of glucose. Let's convert those kilograms to grams and then convert those grams to moles using the molar mass of glucose that I added up off the periodic table. Step 1, step 2, done. Step 3, use the relationship in the balanced chemical equation to convert moles of what we know, glucose, to moles of what we're looking for. And this is where this new term comes up. And some places use this a little bit more, some places use this less, but we've got 1 mole of glucose per mole of reaction, as I've described it here. What is a mole of reaction? Well, if we think about a chemical equation as being a molar chemical equation, right? 1 mole of glucose, 6 moles of oxygen, 6 moles of carbon dioxide, 6 moles of water, then we can sort of describe this happening once as a mole of reaction. So 1 mole of reaction, so it's the reaction as written or the reaction as balanced, in this case has 1 mole of glucose. So I canceled out my moles of glucose, I'm left with moles of reaction. And the reason this is important is because this 670 kcals has to have a number associated with it, or it has to have a unit associated with it. And often when you look it up in a table, it'll be a number that's kilocalories per mole, or joules per mole, or kilojoules per mole. What is that a mole of? Well, that is per mole of reaction as written. So moles of reaction as written gets canceled out, and we've got 670 kcals. That gets us to 6,500 kcals, and I've rounded to correct sig figs here. All of the inputs that I've got, that 670 is what's limiting our sig figs because I don't think that 0 is significant. There's nothing telling me it is, so that's just a 2 sig fig number. We've got 4 sig figs there. We've got 6 sig figs there. This is a defined conversion, so that's infinite. This is an exact ratio, so that's infinite. So we need 2 sig figs. Let's round that to 6,500 kilocalories. So that's one way we can use heat in our thermochemical equation by figuring out how much heat we're going to get out. Another way we can do that is go the other direction. Same chemical equation. How many grams of glucose must be digested to liberate 35,490 kilocalories of energy? So what do we have? We know that we've got, well, there's a balanced chemical equation. That's step one. Step two, how do I get moles? Well, I know this is how much energy I want. And, oh wait, there's moles of reaction because I've got a balanced chemical equation. So this is mole of reaction is 670 kcals. So if I take 35,490 kcals divided by 670 kcals per mole, I get moles of reaction. So that's that second step in our stoichiometry process. So then we're off to the races, right? Now we just need to do, here's this first part, get us to moles. Use the balanced chemical equation to convert moles of what we know, reaction, to moles that we're interested in, glucose, and now get from moles of glucose out to grams of glucose, which is what we wanted. Again, we're stuck with 2 sig figs because of this 670 number. So 9,500 grams or 9.5 kilograms of glucose needs to be burned or digested in order to liberate that much energy. Those are great examples of sort of isolated chemical processes, but in this one, where did that energy come from? Or where does that energy go, right? We're liberating a bunch of energy. Is that energy just diffusing off into the universe and not really worrying about it? It'd be nice if we could make use of that. So the way we make use of that is in something that we usually refer to as coupled systems. So if a reaction liberates heat, where does that heat go? It must go into something, and it'd be nice if we could put it somewhere where it was useful. Likewise, if a reaction requires heat, we need that heat to come from somewhere. So how do we do that? We've got system A and system B, and there's a transfer between system A and system B. Without involving any mysterious new energy coming into or out of the surroundings of these two systems. Using that system and surrounding type of model, we can almost define system A and system B as our universe if we can assume that the heat transfer is perfectly efficient, which, by the way, it's often not. So let's take a look at an example. So let's stick with the same chemical equation so we don't have to mess things up there. So burning glucose, how many grams of glucose must be digested to liberate enough energy to raise the temperature of 500 milliliters of water from 8.61 degrees C to 36.57 degrees C? I've included a number I had to look up. Specific water of liquid water, a specific heat of liquid water is 1 calorie per gram degree Celsius. So here's my coupled system. I'm burning some glucose to liberate energy, and now I'm using that energy, that heat energy, to heat up some amount of water. So there's my coupled system. If we look at the problem, we probably have to start with the water half because that's the one we've got information about. I've got 500 milliliters of water and I want to raise it through this temperature range. So just like with all specific heat problems, let the unit set up your problem for you. 1 calorie per gram degree C. I've got how many grams of water? Well, I've got 500 milliliters of water, and water has a density of 1 gram per milliliter. So these together give me grams that cancel that grams. And how much of a temperature change am I looking at? Well, there's my temperature change. So I need 13.98 kilocalories of heat in order to heat the water the way that I want to heat it in the problem. Where's that heat going to come from? That heat's going to come from burning glucose or digesting glucose. So 13.98 kilocalories from the balanced thermochemical equation. I know that 1 mole of reaction will liberate 670 kilocalories. Balanced, or mole ratio from the balanced chemical equation, that's step 3 in our stoichiometry process. And now back out into grams of glucose. So by burning 3.8 grams of glucose, I will produce 13.98 kilocalories of energy. If I then use that energy to heat water, I will be able to heat 500 milliliters of water from 8.61 to 36.57 degrees C. So again, this is another case where a coupled system problem doesn't have to be one big problem. It can really just be a couple of different small problems that we end up combining after the fact. Keep looking at the steps to get there and challenge yourself with a few of these coupled system problems to see how well you do. I'll see you next time.